Good morning friends, and welcome to the video course on advanced hydrology. In the last class we looked at the dynamics of what goes on inside a cloud. All right, we on the board we looked at a blown up picture of a cloud, the lifting of the air mass, nucleation, and what goes on and how the rainfall comes out of a cloud. Then we looked at the different forms of precipitation, in which we said the precipitation can be in the form of liquid or solid, all right, and various different kinds. Then we moved on to the precipitation characteristics in Indian conditions, and then we said that the season in India, the meteorological season in India is divided into 4 parts, and the most important one of them is what is called the southwest monsoon, and we looked little bit more details into the southwest monsoon in India. Then we moved on and started looking at what is called the terminal velocity. Okay. As the raindrop forms in the atmosphere, it starts to descend towards the ground, all right, and then there are many forces acting on it, and then we started looking at how we can calculate at what velocity the raindrop will fall. Okay. So, let us look at this schematic which we started looking at yesterday. So, we are trying to find out the terminal velocity. Let us assume that there is a spherical raindrop, all right, and its diameter is d, all right, and we said that there are 3 main forces that act on this spherical raindrop as it is falling through the air. First one is the gravity forces, which are acting in the vertical downward direction. Then you have the buoyancy forces, which will be acting in the upward direction as shown in the figure, and then the third one is what is called the drag forces due to the resistance offered by the air. Okay. Now, the diameter we have said is let us say d, and then if we want to write down the expressions for these forces. So, what will be the f of g? Well, it is nothing but the density multiplied by the volume, all right, density of water multiplied by the volume of a sphere of diameter d, that is all it will be, all right, not exactly density, but the specific weight. So, if you see that, it would be rho w times g, that is your specific weight, and then the volume of a sphere of diameter d, as you all know, would be this. Okay. And I am going to number this equation as 331. Okay. So, this is the force or the gravity force or the weight force which is acting or which is pulling this spherical raindrop below. What is the f of b? It will be nothing but the weight of the air or the fluid which is displaced by the object, all right. So, it will be the same expression, except that instead of the density of water we will use the density of the moist air. Okay. So, it will be rho a g times pi by 6 d cubed, and this is 3, 3 and 2. Okay. And what will be the drag force which will be actually acting on the surface area of this whole spherical raindrop, right. From the knowledge of our fluid mechanics, we will take this as C d times rho a times v squared by 2. The drag force that acts on any object is directly proportional to the square of the velocity, and there is a coefficient of drag C d. Okay. And let me number this equation as 333. Okay. And then let me define all the things here. Your rho a is the density of air, rho w is the density of water, C d as we know is called the coefficient of drag or drag coefficient. Okay. D is the diameter we have defined, and A is the cross sectional area of the raindrop. It is not the surface area actually. So, that is how the drag force is defined. It is not rainfall, but the rain drop. Okay. And V is the velocity of fall with which the raindrop would be falling. Okay. Now, as the drop is released, let us say from rest, initially it starts with a 0 velocity, okay. Then it starts to accelerate, all right. After some time, what happens is, initially as it starts to accelerate, the drag forces are minimal, and then they start to increase, because the drag forces are directly proportional to the velocity. So, the drag forces increase, and after some time what will happen is, all the forces will start to balance each other. Okay. So, if you want to write it down in words, it will be, if the raindrop is released from rest, it will accelerate until it reaches what is called the terminal velocity or fall velocity. Okay. And let us denote that as V t, which is what we are trying to find out, at which the three forces will be in equilibrium, will balance out, or will be in equilibrium. So, that what do we have? Your F d and F b are the two forces which are acting in the upward direction, and their sum should be equal to F of g, all right. That is the balance of these forces. So, what we do is, we have these expressions for this, and we put V is equal to V t, all right, and those three expressions, and then what we are going to get, we can simplify that and get the expression for the fall velocity, all right. So, let me try and do that. So, you have C d rho a pi by 4 d square is your cross sectional area, and let us say V t is your fall velocity. So, V t square by 2. This is equal to rho w g times pi by 6 d cube minus rho a g times pi by 6 d cube. So, what I have done is, I have taken the buoyant forces on the other side, okay. And then I will not work out, you can see that easily, that the expression for V t will come out like this. Rho w over rho a minus 1, and this whole thing raised to the power half or square root of this. Okay. So, this is your 3, 3 and 4. Okay. So, this is the final expression from which we can calculate the terminal velocity or fall velocity at which a raindrop of spherical diameter d would fall through the atmosphere. So, you see that if you look at this equation, the fall velocity is directly proportional to the diameter. So, as the diameter increases, its fall velocity will also increase, all right. And then if you see that C d is in the denominator, or the fall velocity is inversely proportional to the C d, all right. So, if the drag force increase, the fall velocity will decrease and vice versa, okay, which is intuitively it makes sense. Okay. Now, this raindrop, which we are actually assuming to be spherical, all right, it is true up to a raindrop of size approximately 1 millimeter, all right. If the size of the raindrop becomes more than a millimeter, then it is no longer spherical, it is oval. If it is more than 1 millimeter, it becomes oval shaped, it is no longer spherical. Well, how do we handle such situations? Well, all we do is we take an equivalent diameter of a spherical raindrop having the same volume, all right. So, then all we do is we take equivalent diameter of spherical raindrop I have the habit of writing rainfall, raindrop it is, having same volume as the actual drop, okay, which is oval in shape. Now, this is as far as the shape of the raindrop is concerned. Okay. Now, let us say assuming that it is spherical. If the diameter of the raindrop increases, do you think that what will happen to the drag force? It will increase or stay constant? Okay. It will obviously increase because the cross sectional area is one of the expressions on the right hand side, all right. However, what we are talking about is it will not increase exactly in that ratio, all right. The coefficient of drag C D itself changes when the diameter increases, all right. So, what we have is C D or the coefficient of drag also increases, all right, as a function of diameter, all right. How does it do? Well, the relationship looks like this. If it is your diameter, it is a nonlinear change like this. Okay. So, the research has shown that the coefficient of drag itself will increase as a function of the diameter of the raindrop. Okay. Now, this relationship of C D as a function of diameter, it is given in table 3.3.1 of the Venti-Chau's book. So, kindly I request you to go through it and look at those numbers, how actually it is changing, all right. So, therefore, we have this final expression for finding out the fall velocity. Okay. Now, what we are going to do is we will look at some of the basic review material which you may have seen in your earlier classes. Okay. As when the rain is falling, all right, how do we measure the rainfall and how do we represent the data, all right. As far as the measurement is concerned, we will not look at it at all because it is an advanced course and you have seen that already. Okay. So, we will get started with how we represent this data which we have collected and how we store it and how we try to understand. So, there are two different forms of data representation we had looked at earlier also, but as far as the rainfall is concerned, we have the first thing is what is called a rainfall heatograph. That is how we represent the rainfall data. Rainfall heatograph. Okay. I am sure all of you understand what is a rainfall heatograph. Okay. Well, it is nothing but it is a plot of rainfall depth or intensity. It is a plot of rainfall depth or intensity as a function of time. All right. And how will it look like? Well, if you see that this is your time domain t and this is your, let us say, I is represented as the centimeters per hour or inches per hour or something like that. Normally, it is represented like a bar chart. All right. So, this is called a rainfall heatograph. I am sure you may have seen this earlier. Okay. So, during a rainfall event, it gives us a very important information about how intensely the rainfall is occurring at different time, all right, which can be very useful in some design purposes. All right. So, this is about the rainfall heatograph, and then you have a rainfall mass curve. Okay. What is a rainfall mass curve? Well, it is nothing but the cumulative value of the rainfall heatograph. All right. So, if we have table in which we have time versus the rainfall intensities or the depth of rainfall in each interval, what we can do is we can just accumulate those values as a function of time. That is what will give us the rainfall mass curve. So, it is the cumulative curve of the rainfall heatograph. Okay. So, if you want to define it, it is a plot of cumulative rainfall depth as a function of time. Okay. And how will it look like? Let us say it is P cumulative and its unit would be some length units. It will be like this. Okay. In the rainfall mass curve, one thing important we should note is that it is an always rising curve. That is, it will never drop down. Okay. So, it is always rising or it will remain constant. All right. When it is constant like this period, what is happening during this period? Well, there is no rainfall during this period. All right. The rainfall depth is increasing as a function of time, let us say from 0 up to this time, whatever that time is. All right. After that, the curve is constant. So, there is no rainfall. Okay. And what is this period? This is nothing but the duration of the rainfall. Okay. So, this is, you can say, is the duration of this particular storm event which occurs between 0 and t. Then there is a period of no rain and then there is some more rain, then there is a period of no rain and then rainfall starts to increase. So, it is a constant curve, continuous curve, which gives you a lot of information about the duration of the rainfall, the depth of rainfall in each interval and also the intensity. We can differentiate this curve, all right, and find out what will be the rainfall intensity at any given time, right. So, it is always very handy and very useful data representation method. Okay. The next thing we will look at is very important, which is called the maximum depth duration curve. Okay. This maximum depth duration curve is useful in hydrologic design. As the name suggests, it gives you information on the maximum amount of rainfall depth that can occur in any given duration. Okay. So, when we are doing some hydrologic design, that is your culvert design or any hydrologic structure is to be designed in a catchment, then we want to find out what is the maximum amount of rainfall that can occur, which will we can then easily convert into the runoff depth. All right. So, those things are designed for peak discharges, which will depend upon the maximum intensity and the maximum rainfall. Right. So, that is how it is very useful in hydrologic design of certain hydraulic structures. Okay. Now, how do we find this maximum depth for certain duration? All right. Well, what I would like to do is I will give you a step by step procedure first to determine or to find this maximum depth duration curve, from which we can deduce the maximum intensity duration curve also. All right. And then we will look at a solved example or a numerical example of this. All right. So, the steps that are involved in this are, let us say what we need is, using all the data that are given to us, we develop a rainfall mass curve using data of the most severe storm. Okay. So, when you are trying to find out the maximum depth that can occur in a duration, you want to take the data which is the most severe in a particular catchment. For example, you have a catchment in which you want to find out this maximum depth duration curve. So, what we do is, we just scan through all the data that are available to us. We may have 20 years of data available to us, we may have 50 years of data available to us. So, we scan through all the data and then we pick up one storm event which is the most severe as far as the intensities and depths of the rainfall is concerned. Okay. So, we select that and then develop a mass curve of that, okay, and we have just seen what is a mass curve and how we can calculate it. So, once we have that mass curve, what do we do? The next step then is select suitable or certain, I should say desirable, durations, all right, durations for which we want to determine the maximum depth. All right. There can be different durations which are important from hydrologic design purposes. For example, a 2-hour event is what is very important, because you want to design a certain structure for a 2-hour event which are predominant in a catchment. So, these durations can be any duration, for example 5 minutes, 10 minutes or even hours, etc. Okay. So, we select those durations depending upon our need, all right, or the practical purpose. Now, the next point which I am going to write is extremely important to understand. For each duration, compute the max rainfall depth by, how do we do that? By subtracting cumulative rainfall depths and how do you select those? Between times having the selected duration. Okay. So, what you do, what this step is saying is, let me read it once more and then I will come back and try to explain you. For each duration, compute the maximum rainfall depth. How? By subtracting the cumulative rainfall depths between times having the selected duration. Okay. So, what you are doing is, you have the rainfall mass curve with you. Let us say you have selected a 5-minute duration for which you want to find out the maximum depth. All right. So, for 5-minute duration from the mass curve, what you do is, you subtract the two values which are separated by 5 minutes. All right. There may be many of them. For example, you may have the values between or at intervals of 5 minutes. So, you have the cumulative rainfall at 5, 10, 15, 20, 30 and so on minutes. So, what you do is, you keep on subtracting the cumulative rainfall depth values at 5 minutes. So, 5 minus 0, 10 minus 5 and so on. Okay. So, you will have that column, and that in that column you determine which is the maximum. All right. So, that will be your maximum depth for a 5-minute duration. So, this is the procedure. I would like to take up an example to explain this further. Okay. And then what you do is, you repeat this exercise for other different durations which you have selected. So, you say you repeat the process for all and once you have the maximum depth for all the selected durations you have the maximum depth duration curve, right, and you can convert those maximum depth for each duration into intensities, right. So, then you can develop easily maximum depth duration curve, and then also you can develop the maximum intensity that can be expected for each duration curve. Okay. So, this is the procedure for finding out the maximum depth duration or maximum intensity duration curve, all right. So, now what I will do is I will take up an example. Okay. So, for that first I would like to write it for you, so that you understand what the problem is, and then I will go to the board and try to solve it. Okay. So, we are looking for an example on this maximum depth duration curve. Okay. This is how it goes. A very severe rainfall event started at, let us say, 11 a.m. somewhere, okay, on a certain day. The incremental depth of rainfall for every 10 minutes during the storm were observed as, these data are given to us. During the first 10 minutes it was 1, during the next 10 minutes it was 3, and then next 10 is 7, and so on. So, you have 10, 7, 5, 2, all these values are in mm or in millimeters, and then the storm stopped. The rainfall event stopped abruptly. Okay. Answer the following. A, what is the duration of the storm? That is part A. Then B is estimate and plot the rainfall heatograph, or I will just say heatograph in this case, and what are the units in which you have to do in millimeters per hour versus minutes. Okay. The third part is estimate and plot the mass curve. Okay. And the units should be millimeters versus minutes, and D, estimate and plot the maximum depth duration curve, which the procedure we have just seen, the maximum depth duration curve, and lastly E, estimate and plot the maximum intensity duration curve. Okay. So, what I am going to do is I will demonstrate this on the board, and I am not going to plot all these different plots which have been asked. All right. So, all we will do is we will just estimate or calculate these different curves, and then you can go ahead and plot them. We will just roughly sketch the final two. Okay. So, now I am going to go on the board and look at this example how we can solve it. So, first we will put on all the data here which are given to us. You have 0, all the data are given at 10-minute interval. So, you have 10, 20, 30, 40, 50, 60, 70 and 80. In each 10-minute interval, the rainfall depth P that is given to us in millimeters. All right. During the first or at 0 there is nothing, so it is 0. Then I will just write all the numbers which are given in this problem, which is 137, 10, 752 and 0. Okay. So, there is rainfall up to 70, and after that in the next interval there is no rainfall. All right. So, these are all the values given to us 1, 3, 7, 10, 7, 5, 2. Okay. Now, first thing we need to calculate is the intensity of rainfall, and that is in millimeters per hour. Okay. So, what will be the intensity? At 0, of course, you will have 0 everywhere. All right. So, you have 1 millimeter of rainfall occurring in 10 minutes. So, what will be the rainfall occurring in 1 hour? All right. You can easily calculate it. All right. So, all you will need to do is it will be 6 times of this, because this is 10 minute, you want to find out in 60 minutes. So, it will be 6 times of this column. All right. So, all you need to do is to calculate the intensity of rainfall during this storm event. You just multiply this column by 6. So, I am just going to do that. So, you will have 6, 18. So, this is the intensity in millimeters per hour. So, you have 42, 60, again 42, 30 and 12, and then 0. There is nothing during the last interval. The next column which we will actually need for the maximum depth duration analysis, what will be the cumulative rainfall, cumulative P in millimeters. Okay. At 0 it will be 0, of course. All right. What will be the cumulative rainfall for the first 10 minutes? All right. So, now we will be looking at this column, because this gives you the rainfall depth at each 10 minutes, and you want to accumulate these values. So, it will be this plus this, so which is just 1. Okay. So, the value or the cumulative rainfall depth at 20 minutes will be equal to what? This value plus what occurs between 10 and 20. All right. So, it is 1 plus 3, that will be equal to 4. Okay. This process should be very clear. All right. How we calculate the cumulative value of rainfall. Similarly, it will be 4 plus 7, that is 11, and we keep on doing it. All right. So, it will be 21, 28. You see that they will be increasing all the time, it will not be decreasing. 33, because it is always a rising curve. 35, and then it remains 35. Okay. There is no rainfall between 70 and 80 minutes. All right. So, the cumulative depth of rainfall is what? 35 plus 0, which is 35. So, it will remain constant if it does not rain. Okay. So, what are your answers then? As far as the first part is concerned, A is the duration D. What is the duration? Can somebody tell me? the duration of the total rainfall, all right, is what? It starts from 0, there is some rain between 0 and 10, all right, and then at 70 minutes there is some rainfall, but after that it does not rain, all right. So, the duration as you see will be 70 minutes. That is your A part. Okay. What was B? B was your rainfall heatograph, all right. So, this is your answer B, time versus intensity of rainfall in millimeters per hour versus the duration, all right. So, at these times these are the rainfall intensities. Okay. Part C I think was what is the cumulative or the mass curve. So, it is this your answer C. Okay. This is your, so let me just write it down somewhere that this is your answer B and this one is your answer C. Okay. Now, we move to D and E, in which we have to calculate the maximum depth duration curve. Okay. So, all right. So, what we will do is we will write this for all the durations we have starting from 10, 20, 30 all the way up to 70 or 80. Okay. So, let me just write it and then we will see how we can calculate it. So, you have 10, 20, 30, 40, 50, 60, 70 and 80. Okay, so we are looking at how we can determine the maximum depth duration curve now, all right. So, we will start with the duration of 10 minutes and then we will do it for 20, 30 and so on. Okay. So, for 10 minutes initially when we have a 0 there will be nothing, all right. So, for 0 you can put a dash for all of them, all right. So, now we focus on the 10-minute duration. What is the maximum depth that can occur in 10 minutes, all right. And what is the procedure? Well, we take the mass curve which is this one. Okay. So, this is our mass curve and now what do? We subtract the cumulative depths which are separated by 10 minutes. So, this is our focus of attention is 10 minutes. So, the successive values are at 10 minutes. So, 1 minus 0 is what you put here, then 4 minus 1 is what you will put here and so on, okay, which actually will come out exactly this in this particular case. So, if you did that you will have 1, 3, 7, what is 7? It is 11 minus 4, all right, that is what we are doing, okay, and we will keep on doing it for other minutes also. Okay. So, this is 10, 7, 5, 2 should be easy to see and 0. Okay. So, how is this 0 coming? 35 minus 35, all right, 35 minus 33 is 2, 33 minus 28 is 5 and so on. Okay. So, these are the depths which occur in 10 minutes. What is the maximum? Well, you just circle that. So, the maximum depth that occurs in 10 minutes is 10 millimeters, and when does it occur? Between 30 and 40 minutes. Okay. So, this is how we find the maximum depth for any duration. Now, we do it for 20 minutes. So, for 20 minutes the first 10 minutes you do not have anything. So, you can put a dash everywhere actually. Cumulative depths which are separated by 20 minutes. So, you have 4 at 20 and 0 at 0. So, you will have these are separated by 20. So, then you have 4 minus 0. So, that will be 4 will come here. The next one is 11 is at 30 and then 1 is at 10. The difference is 20 minutes, right. The difference in cumulative rainfall depth is what? 11 minus 1 is 10. Okay. Similarly, the next one it will be 21 minus 4 which will be 17 and you keep on doing this. Okay. next one also will be 17, then you have 12, 7 and 2. Okay. What is the maximum? Well, it is 17. So, you do the same thing for 30. So, one more row you can just say that there will be no value at 20, because we are working on 30 onwards. So, you have for 30 I am just going to write it directly. So, it will be 11, 20, 24, 22, 14 and 7. Okay. The maximum is 24, the next one is 40, all right. For that it will be 21, 27, 29, 24 and 14. The maximum is 29, and we can keep on doing this. For the next one, which is 50 minute, it will be 28. You can verify that, and we are using exactly the same procedure, 31 and 24. So, it will be 32 for the 50 minute duration, and for 60 you would have 33, 34 and 31. This is maximum, these two there is nothing, and for 70 you would have 35 and 34. Maximum of course is then for 70 minute duration is 35, there is nothing here, and then the last one will be 35. Okay, so, we have seen that how we can calculate the depths at different durations, and in each column we can find out what is the maximum depth. All right. For 10 minute duration, the maximum depth is 10 millimeters. For 20 minute duration, the maximum depth is 17 millimeters, and then so on. So, what we can then do is we can just write down this maximum depth duration curve in a tabular form, and then we can plot it. Okay. So, you have time is equal to, you have 0, 10, 20, 30, 40, 40. Okay. So, for 10 you have this maximum depth, this is in millimeters. For 0 obviously it is 0. Okay. For 10 minutes we have 10 millimeters, for 20 we have 17 millimeters, all right, it is coming from here. For 30 minute duration the maximum depth was 24, okay, and so on. We can keep on writing. So, I will just quickly write it 29, 32, 34 and it was 35 and 35. Okay. So, this is your maximum depth duration curve, right. Now, the last part in this question is find out the maximum intensity duration curve. Okay. And how do we do that? Well, we just divide these depths, all right, these are the maximum depths, and if you want to find out maximum intensity, what do? You divide the depth by the duration or the time frame, all right. So, for 10 it will be 10 minutes, so you divide this by 10. For 17 it is 20 minutes, so you divide this number by 20, all right, and then so on. So, that will be your intensity in millimeters per minute, all right, and if you want then you can convert it into per hour, all right. So, the intensity we have to find is in millimeters per hour, all right. So, you have 10 millimeters depth of rainfall occurring in 10 minutes. So, how much it will occur in 1 hour, all right, that should be very easy to find out. Okay. So, if you did that, you will have maximum intensity duration curve as you can see, how much will it be? It is 1 millimeter per minute. So, it is 60 millimeters in an hour, all right, and then you can keep on calculating this. So, 51, 48, 40, 3.5, 38.4. So, you see that it will be constantly decreasing. Okay. 38.4, this is 34, 30, and for the last one it will be 26.5 millimeters per hour. Okay. So, if you want to just look at how it will look like, so what we can then do is we can plot this maximum depth duration curves and maximum intensity duration curves. All right. So, this is your duration in minutes, and on the y axis we plot the maximum depth. Okay. So, you see that for 0 the depth is 0. So, this is your one point. At 10 minutes you have 10. All right. So, I am not going to scale it, but you can see that it will be somewhere here, and then you can take all these points and it will be something like this. Okay. If you plot all those points at different times what is the maximum depth, you will have this maximum depth duration curve. So, this is your okay. The other one is the maximum intensity duration curve, and the intensity is in millimeters per hour. All right. So, you will have at 0, actually it will be infinity, it will not be 0. All right. So, we will not plot it. So, at 10 you will have a value is 60, which will be maximum, and then it will in fact go down like this. Okay. So, this is your maximum intensity duration curve. Okay. So, we have seen that using the data from a rainfall mass curve, how we can determine various storm characteristics such as the duration, the hyetograph, the mass curve, and also the maximum depth duration and the maximum intensity duration curves. Okay. Okay. The next thing we will do is look at another concept which is called the IDF relationship. Until now we have looked at the intensity duration relationship. Now we are throwing another dimension which is called the frequency. I is intensity, T is duration, and F is frequency. All right. So, if I plot a curve which is duration and this is your depth. So, first we look at the maximum depth duration frequency curve, and then we will look at the maximum intensity duration and frequency curve. Okay. So, as I said, we have thrown another dimension here which is capital F. What is this? F is frequency. So, we just looked at what is the maximum depth duration curve, but if we analyze any event which has a different frequency, and how do we measure frequency in hydrology? Well, I am sure you may have seen something called return period or the recurrence interval. All right. If you have an event which can occur once in 10 years or once in 50 years or once in 100 years. All right. So, that is how we represent the frequency of an event. All right. So, let me plot 3 curves here. Okay. These are maximum depth duration curves. Okay, for 3 different return periods, and if I tell you that one of them is for 100 years, other is for 50 years, and one of them is for let us say 10 years, okay, or 25 years. Which one will be which? All right, there are 3 curves here. One is for a higher frequency, other is for a lower frequency, and one is in the middle. And from your knowledge, you understand that the event which is rare will have higher magnitude. For example, a 100-year flood will occur less frequently, isn't it? Similarly, if you have a 10-year flood, that will occur more frequently, but its magnitude will be smaller. All right. So, you have the higher value here. All right. So, you can say that this will be for 100 years. All right. Its frequency is less, it will occur once in 100 years. This one is 50 and this one is 25. Okay. Now, on this one I plot the maximum intensity duration frequency curves, all right, in which again you have 3 different frequencies with which these occur. The same logic will apply. The first one is for 100-year flood or 100-year recurrence interval, rather I should say. The middle one is for 50 and this is for 25. Okay. And these are your depth, intensity, duration, frequency curves. Okay. So, you see that we can carry out this intensity duration analysis and then we throw another dimension of frequency, and the frequency we measure in terms of the return period, all right, and higher the return period, higher will be the magnitude of the maximum depth and the maximum intensity associated. Now, IMD has carried out lots of studies on Indian conditions, in which they have tried to develop a relationship which gives you this IDF curves or IDF relationships that are called. I will just give you this and then we would stop here today. So, this maximum intensity is given as this implicit equation KTX over D plus A to the power n, where I is in centimeters per hour, capital T is your frequency in terms of return period in years, and D is the duration of your rainfall event in hours. Okay. So, this is the relationship the IMD has developed for Indian conditions, in which there are 4 parameters you can see, which is your K, X, A and N are defined for different regions in India. Okay. So, if you have or if you want to find out the maximum intensity, all right, for a certain duration storm, all right, for certain recurrence interval, all right, you can just select the values of these parameters, that is K, X, A and N, and put those values in this equation. It will give you the maximum intensity. All right. How these have been developed? Well, we looked at this procedure, and all these procedures have been followed for lots of rainfall data for Indian conditions. Okay. So, what I would like to do is stop here today, and then in the next class we will start looking at the spatial averaging of rainfall. you.